Okay, so gravitational potential energy, phi, okay, at a point in a gravitational field is defined as the work done in moving a unit mass from infinity to the point. So let's say we had an object here, here's my object, and it is at infinity. Here's my sort of Earth, okay, or sort of planet, and I'm going to move this object towards the planet and stop it at a certain distance. Okay. So now what is the work done? Is there a gain in energy on the object, or is there a loss of energy on the object? Okay, so let's have a think about that. So hopefully you said that the thing is going to lose energy, okay, have a loss. So it's going to lose energy as it goes down here. It's like falling down towards a table. It's going to lose gravitational potential energy. At the bottom, remember we're going to stop it, so there's no kinetic. So we actually have to remove all the energy. Now, the important thing to note here is that at infinity, the gravitational potential energy is 0. So we're actually going to lose energy from 0. Very interesting that. We'll talk a bit more about that soon. But what's the formula for this? Well, it's work done per unit mass. So phi is equal to work done per unit mass. Okay. What's the unit? Well, it's joules for every kg. Essentially we can say if we had an object here and we knew it's phi, we'll know how many joules it possesses for every kg. Okay, so actually deriving the thing is quite complicated. We'll just skip through it. So what we have here is moving the object from A to B, like we mentioned before. Now here's the object here, it's at a distance r. Now work done is equal to force times distance. So in this case the force is the gravitational force, and we're multiplying it by the change in distance towards the mass. Now you might notice that because this is not a linear change, that we're going to have a curve, okay, in terms of the energy. Now because we have a curve, we want to actually find work done. It is a force distance curve here. We need to find the area under that curve. Okay, is use a bit of algebra. Okay, so not really, you don't really have to know precisely how to do this, but just have awareness that by integrating you can find that area. Okay, what we're left with is this formula here for the work done. Okay, so that's essentially it's going to be what energy it has. Okay, what sort of potential energy, and you see it's actually a negative. So in other words, it actually goes from 0, which is the energy at infinity, because there's no gravitational attraction at infinity, so it can't possess any potential energy. It can't actually do anything. If you left it there at infinity, it wouldn't move. However, if you bring it in slightly, it then does have some potential energy. And what happens is it loses potential energy. So it needs to actually lose potential energy as you come towards the object. So here's the object on the the y-axis, and we're starting off at 0 and we're actually losing energy. So the energy is actually negative. So what we're saying here is essentially talking about that negative thing, and we know what the work done is, so we're just putting that into there, okay, for the phi formula, and effectively you get this formula for phi. So a bit of a formula summary. Let's change colours. So Newton's law of gravitation, F equals G m1 m2 divided by r squared. Gravitational field strength, G equals force per unit mass. However, substituting in your Newton's law of gravitation, you can get G equals G m1 divided by r squared. That's an F. Gravitational potential energy, EP, equals mgh over a small distance. Okay, small distance, small distance, small distance. Or you could have it as EP equals negative G m over r, and then what's gravitational, not gravitational energy, gravitational potential is going to be phi equals W over m, or phi equals G m over r, whoops, can't write down there, r, and make it a negative. There's all your formulas. What we're going to discuss is these things in class.